So good afternoon, students. This is Arvind, Assistant Professor, Department of EEE, DBS Kavali. So in the previous session, I discussed about the second unit of the facts, that is voltage source converters and current source converters. Mainly, I discussed about the current source converter concepts, and now from onwards, I am going to discuss the third chapter, that is static shunt compensators. Okay, so firstly, I will give the index of that this chapter, that is firstly these are the contents we are going to cover in this chapter. That is, first one is objectives of shunt compensation. So the unit name is static shunt compensators. So in that one we have to cover these concepts. Firstly, I will cover the objectives of shunt compensation. So it consists of different objectives, that is midpoint voltage regulation for line segmentation and end of line voltage support to prevent voltage instability and improvement of transient stability and power oscillation damping and summary of compensator requirements. Okay, next we have methods of controllable VAR generation. So here we have different methods. Those are variable impedance type static VAR generators, and next one is switching converter type VAR generators, and next hybrid VAR generators. Those are switching converter with TSC and TCR, that is a thyristor switched capacitor and thyristor controlled reactor, and summary of static VAR generators. And next we have static VAR compensators. Those are SVC and StatCom. So actually these concepts I covered briefly on the first chapter of the flexible AC transmission systems. Okay, in that one we have the regulation slope and transfer function and dynamic performances and transient stability enhancement and power oscillation damping and VAR reserve, that is operating point control, and summary of compensator control. Okay, next finally we have the comparison between StatCom and SVC. So in that comparison we have different comparisons, that is VI and VQ characteristics, that means voltage current characteristics and voltage and reactive work characteristics. And next we have transient stability and response time and capability to exchange real power and operation with unbalanced AC system and loss versus VAR output characteristics and physical size and installation and merits of hybrid compensator. And finally we have the static VAR systems. So this is the main concepts in the, these are the main concepts in the third chapter, that is static shunt compensators. Firstly, I am going to discuss the objectives of shunt compensation. Okay, so firstly I will start with the what is the shunt compensation, why we require this shunt compensation in the FACTS controllers. Okay, so actually it has been recognized that the steady state transmittable power can be increased and the voltage profile along the line controlled by appropriate reactive shunt compensation. Okay, so it has been recognized that the steady state transmittable power can be increased and voltage profile along the line controlled by appropriate reactive shunt compensation. So the purpose of this reactive compensation is to change the natural electrical characteristics of the transmission line to make it more compatible with the prevailing load demand. Next, thus shunt connected fixed or mechanically switched reactors are applied to minimize line over voltage under light load conditions. So the shunt connected fixed or mechanically switched capacitors are applied to maintain voltage levels under heavy load conditions. So here we are considering the two cases. One is when we use the shunt connected fixed or mechanically switched reactors. These are applied because to minimize line over voltages, to minimize line over voltage under light load conditions, and the shunt connected fixed or mechanically switched capacitors are applied to maintain voltage levels under heavy load conditions. Okay, that's why we are using the switched reactor and switched capacitors. So mainly these two are used in the our common concepts. Okay, next, so in this section the basic considerations to increase the transmittable power by ideal shunt connected wire compensation will be reviewed. So this is the main objective for our chapter, that is basic considerations to increase the transmittable power. Okay, by ideal shunt connected wire compensation will be reviewed in order to provide a foundation for power electronics based compensation and control techniques to meet specific compensation objectives. So we have different compensation objectives. Okay. So in this section, I am going to cover those concepts only. Okay. Next, so the ultimate objective of applying reactive shunt compensation in a transmission system is to increase the transmittable power. Okay, the ultimate objective of applying reactive shunt compensation in a transmission system is to increase the transmittable power. So this may be required to improve the steady state transmission characteristics as well as the stability of the system. Okay, this may be required to improve the steady state transmission characteristics as well as the stability of the system. Next, so the wear compensation is thus used for voltage regulation so here we have the four objectives of the shunt compensation. Those are at the midpoint to segment the transmission line. So at the midpoint to segment the transmission line, this is one of the objective, and at the end of the line to prevent voltage instability. At the end of the line, that is also known as radial line, to prevent voltage instability. So as well as for dynamic voltage control to increase transient stability and damp power oscillations. Okay, so here we have to increase the transient stability and damp power oscillations. So these are the main objectives in the shunt compensation. I am going to discuss these objectives one by one. Firstly, I am taking the first one, that is at midpoint. So at midpoint, so this is the midpoint voltage regulation for line segmentation. So midpoint voltage regulation for line segmentation. So here I am considering the simple two machine transmission model. That means here I am taking two buses in which an ideal wear compensator is shunt connected. So here in this one, I am taking an ideal compensator, that is here the power is 0. P is equal to 0 is shunt connected at the midpoint of the transmission line. So this is the diagram. This one is shown in the diagram. So this is the diagram we have. So on the right side and on the left side, we have the sending and receiving end voltages, that is Vs and Vr. And next we have reactances x by 2 and x by 2. Total we have the reactance x value. And here I am taking at the midpoint of this transmission line, that is a ideal wear compensator. It is shunt connected to the transmission line. Okay, it is shunt connected to the line. So it consists of ideal wear compensator. It consists of the power is 0. So here the current is flowing, that is ISM and IMR. So ISM is the midpoint from sending end to midpoint to current, and IMR is the midpoint to receiving end current. And here we have VM, that is the midpoint voltage. Okay, so this is the diagram what we have what we are using in the midpoint voltage regulation for line segmentation. So here I am taking, so for simplicity, the line is represented by the series line inductances. So here in the diagram I am taking two inductances, each one consists of x by 2 value. So for simplicity, the line is represented by a series line inductances. So here the compensator is represented by a sinusoidal AC voltage source. So here I am taking a AC voltage source, that too sinusoidal. It is used for the fundamental frequency. So the AC voltage source in phase with the midpoint voltage, that is Vm, and with an amplitude identical to that of the sending end and receiving end voltages. That means here the midpoint voltage is equal to sending end voltage, so that is equal to supply voltage, that is V. Okay, so the midpoint compensator in effect segments the transmission line into two independent parts. So the midpoint compensator in effect segments the transmission line into two independent parts. That's why we are using two inductors with a value x by 2. Okay, so the first segment with an impedance of x by 2 that carries power from the sending end to the midpoint, and the second segment also with an impedance of x by 2 carries power from midpoint to the receiving end. Okay. Next, the relationship between voltages, that is the sending end voltage, receiving end voltage, and midpoint voltage, and line segment currents, that is ISM and IMR, is shown by this phasor diagram. So here I am taking a phasor diagram. It gives the relationship between the voltages and line segment currents. Okay. So here we have different voltages and different currents. So here the magnitude of the sending end voltage and receiving end voltage and midpoint voltage is equal to supply voltage V. So here I am having a angle difference that is delta by 2. So it consists of the sending end voltage and midpoint voltage and receiving end voltage on the two lines. Okay, so here we will have a voltage of sending end sending end to the midpoint and midpoint to the receiving end voltages we have, and also we have the currents that is ISM and IMR. So ISM is sending end to the midpoint voltage and midpoint to the receiving end currents. Okay, so these are consists of the equal inductance value, that is x by 2 and x by 2. So here the inductance and current is combined with, that is jx by 2 into ISM and jx by 2 into ISR or IMR. Okay, so these are the concepts. So by using this phasor diagram, we are going to derive the relationship between these voltages and line segment currents. Okay. Next, so note that the midpoint wire compensator exchanges only reactive power with the transmission line in this process. Okay, the midpoint wire compensator exchanges only reactive power with the transmission line in this process. So for the lossless system is assumed. So the real power is the same at each terminal, that is at sending end and at midpoint and at receiving end of the line. It consists of the same real power. Okay, and it can be derived readily from the phasor diagram, that is from the diagram B. So we have VSM and VSR is equal to V cos delta by 4. So from this one I am writing the line segment currents, that is ISM and IMR, that is equal to I. So that is equal to 4V by X into sine delta by 4. So here the angle is delta by 2, delta by 2. Okay, total we have the angle delta. So this is treated as a first equation, and the transmitted power, that is P is equal to, you know the formula, that is P is equal to V into I. So here I am taking P is equal to V into I. So here P is equal to VSM into ISM, that is equal to VMR into IMR. So that is equal to V into I into cos delta by 4. V into I into cos delta by 4. This is treated as another equation. Next, the midpoint voltage regulation for line segmentation. So here the power will be written as P is equal to 2 into V square X into sine delta by 2. And simply we will write, similarly I am writing the reactive power, that is Q is equal to V into I into sine delta by 4. So that is equal to 4V square by X into 1 minus cos delta by 2. So these are the another equations we have. So here the relationship between real power P and reactive power Q and angle delta for the case of ideal shunt compensation is shown in the below diagram. So here I am showing one characteristic diagram. So here the curves is drawn between the real and reactive power and the angle delta. So here I am considering the two cases mainly. So here I am taking the delta angle between 0 to pi, and the power is between P maximum to 4 into P maximum, that is 4 times to the maximum power. Okay, so here I am taking the three curves. Okay, so the first curve consists of the maximum power at P is equal to V square by X into sine delta, and again we have the reactive power at P point, so that is equal to 2V square by X into sine delta by 2. And we have finally the reactive power, that is QP is equal to, that is occurred at the 4 times of the maximum power, that is QP is equal to 4 into V square by X into 1 minus cos delta by 2 or cos delta. Okay, like that we will form the characteristic diagram. So here we have the maximum power is in between 0 to pi, and here, and after that we have the real power at point P, that is 2V square by X into sine delta by 2. So here the power is increasing manner, the power is in the increasing manner up to double 2 times the maximum power, and finally we have the reactive power, that is also between 0 to pi, but here the curve is increasing up to the 4 times of the maximum power, that is reactive power QP is equal to 4 into V square by X into 1 minus cos delta. Next, so it can be observed that the midpoint shunt compensation can significantly increase the transmittable power. So from the previous characteristic diagram, we will observe that the midpoint shunt compensation can be significantly increase the transmittable power, that is doubling its maximum value and 4 times to the maximum value. So at the expense of rapidly increasing reactive power demand on the midpoint compensator. So that is and also on the end generators. Okay. So next, it is also evident that for the single line system of the first diagram, the midpoint of the transmission line is best location for the compensator. So at the diagram, we will have the sending end and receiving end points. So on the sending end, we have the sending end voltage, that is Vs, and after that we have the receiving end voltage, that is Vr. Okay, so in between these two, we are putting an ideal shunt compensator. It consists of the power is 0 and it consists of a midpoint voltage, that is V. So that is the best location. So that is the best location for the compensator in the transmission line. So that is the midpoint. The location is midpoint. So this is because the voltage sag along the uncompensated transmission line is the largest at the midpoint. The voltage sag along the uncompensated transmission line is the largest at the midpoint. So also the compensation at the midpoint breaks the transmission line into two equal segments. I already discussed that one. Okay, for each of which the maximum transmittable power is the same. For the two segments, the maximum transmittable power is same. Okay. And next, so for unequal segments, the transmittable power of the longer segment would clearly determine the overall transmission limit. So actually, we will divide it into two segments. So the two segments equally equally divided. For suppose if it is divided into unequal segments, so the transmittable power of the longer segment would clearly determine the overall transmission limit. So the concept of transmission line segmentation can be expanded to the use of multiple compensators. So actually, in the first case, I am used only for the only one compensator we are used. But after that, in the coming slides, I will show the diagram. It consists of the multiple compensators. So actually, in the previous case, I am used only one ideal compensator at the midpoint of the circuit. But next, I will show the diagram. It consists of the I think 4 line segments I will show. Okay, so the concept of transmission line segmentation can be expanded to the use of multiple compensators located at equal segments of the transmission line. So as illustrated for here, I actually said that this one. So I will take 4 line segments in the diagram. I will show the diagram. So theoretically, the transmittable power would double with each doubling of the segments for the same overall line length. Okay. So furthermore, with the increase of number of segments, the voltage variation along the line would rapidly decrease, approaching the ideal case of constant voltage profile. Okay. So approaching the ideal case of constant voltage profile. So this is the midpoint voltage regulation for line segmentation. So this is the one example. I already said this one. So actually I am taking the two lines, two edges. So on the sending end and receiving end, we are using an alternating voltage source, that is AC voltage source. It is also a sinusoidal, but here I am taking 4 segments. Okay, 4 line segments. Each consists of the reactance value, the inductance value is x by 4. Okay, so the first segment consists of the V1 voltage, and second segment consists of the VM voltage, and the last segment consists of Vn and sending end voltage and receiving end voltage. Okay, and it also consists of the currents, that is ISL and ISM and IMN and INR. Okay, like that we have. And below to the circuit diagram, we have one phasor diagram. We have one phasor diagram. It gives the relationship between the voltages and line segmented currents in the four line segment line. It consists of 4 ideal compensators. Okay. So it is to be appreciated that such a distributed compensation hangs on the instantaneous response and unlimited wear generation and absorption capacity of the shunt compensators employed. Okay, so here I am using a distributed compensation hangs on the instantaneous response. It can and unlimited wear generation and absorption capability of the shunt compensators is employed. So which would have to stay in synchronism. Actually, these are all in synchronism with the prevailing phase of the segment voltages and maintain the predefined amplitude of the transmission voltage independently of load variation. Okay, so such a system, however, would tend to be too complex and probably too expensive. So, to be practical, particularly if stability and reliability requirements under appropriate contingency conditions are also considered. Okay. Next, so however, the practicability of limited line segmentation using thyristor controlled static wire compensators has been demonstrated by the major 600 mile long and 735 kV transmission line of the hydrocubic power system built to transmit up to 12,000 megawatts power from the James Bay Hydro Complex to the city of Montreal and to neighboring US utilities. So here I am taking one example by considering the limited line segmentation using thyristor control static wire compensators. It is been demonstrated by the major. So here I am taking 600-mile long and 735 kV transmission line of the hydrocubic power system built to transmit up to 12,000 megawatts power from the James Bay Hydro Complex to the city of Montreal and to the neighboring US utilities. So here I am transmitting the power from the James Bay Hydro Complex to the city of Montreal and to the neighboring US utilities. So more importantly, the transmission benefits of voltage support by controlled shunt compensation at strategic locations of the transmission system have been demonstrated by numerous installations in the world. Numerous installations in the world. So here the midpoint voltage support of a two machine transmission power system discussed above. So actually we discussed the two machine transmission power system midpoint voltage support above can be easily extended to the more special case of radial transmission line. So indeed if a passive load consuming power P at voltage V, so actually the midpoint voltage support of a two machine transmission power system is easily extended to the more special case of radial transmission. That is the next case. We are going to discuss that one also. So indeed, if it is a passive load, it consumes power P at voltage V is connected to the midpoint in place of receiving end part of the system. Okay, in place of receiving end part of the system, I am connecting this one. Okay, so that also comprises the receiving end generator and transmission link X by 2. And the sending end generator with X by 2 impedance and load would represent a simple radial system. So here I am taking a radial line system. It consists of a passive load. It consuming power, real power P at voltage V. It is connected to the midpoint in place of receiving end part of the system. So it comprises of receiving end generator and transmission link X by 2. So the sending end generator with X by 2 impedance and load would represent a simple radial system. So clearly, without compensation, the voltage at the midpoint, that is at the receiving end, would vary with the load. Okay, that means at the load power factor. So a simple radial system with feeder line reactance of X is here. Okay, so here I am taking a simple radial system with feeder line reactance X. So here I am using this one X and load impedance Z. So this one. So here I am showing the two diagrams. On the left side I am discussing about the left side diagram. So it is a simple radial system with feeder line reactance X and load impedance Z. Okay, so is together with the normalized terminal voltage V. Okay, terminal voltage V versus P plot at various load power factors ranging from 0.8 lag and 0.9 lead. So on the right side we have a characteristic diagram. The diagram is drawn between the voltage, the terminal voltage V versus power P. So here I am taking the values in the per unit. So here the P value is varies between 0 to 1.5 and the voltage value is vary between 0 to 1. So here I drawn a curves characteristic diagram between the loads, that is 0.8 lagging and 0.9 lead. So here we have this diagram, these curves. So first one is for the 0.8 lag and the next one is for the 0.95 lag and the next one is for the unity power factor and next one is for the 0.97 lead and next one is for the 0.9 lead. Like that we are taking the curves. Okay. Next, so the nose point at each plot. So the nose point means this one, the end points. So the connection of the two lines. So this one. Total we have the 5 nose points at a different power factor loads. Okay, the nose point at each plot given for a specific power factor represents the voltage instability corresponding to that system condition. So it should be noted that the voltage stability limit decreases with inductive loads and increases with capacitive loads. Okay, so inductive loads means lagging power factor and capacitive load means leading power factor and resistor load means it is a constant load. Okay, so the inherent circuit characteristics of the simple radial structure and the receiving end voltage versus power plots shown clearly indicate that shunt reactive compensation can effectively increases the voltage stability limit by supplying the reactive load and regulating the terminal voltage, that is V minus VR is equal to 0. So this is also illustrated in the diagram 5.3b. So here, okay, so this one. So here I am taking same. So here I am taking the radial line with X, with the inductance that is X and with the load impedance Z, and it consists of a wear compensator. So actually in the previous case there is no wear compensator, but here I am adding the wear compensator, okay, into the system, and on the right side we have the diagram. So that is the extension of this limit by the reactive shunt compensation. So previously I shown one characteristic diagram versus P versus V. So at that time we are not using the wear compensator. At that time we have the curves like these, and after adding the reactive shunt compensation to the system, the curves are like this. Okay, so here the real power limits from 0 to 1.5 and voltage is 0 to 1, and the limits also, and the power load power factor is 0.8 to 0.9, 0.8 lag to the 0.9 lead. Like that we have the curves. Okay, after adding the wear compensation, the curves is like this and the system is like this. Okay, next, so it is evident that for a radial line, the end of the line where the largest voltage variation is experienced is the best location for the compensator for the radial line. So if it is a midpoint line means the mid part of the system is the best location for the line. Okay, compensator. So next, reactive shunt compensation is often used in practical applications to regulate the voltage at a given bus against load variations or to provide voltage support for the load when due to generation or line outages the capacity of the sending end system becomes impaired. The capacity of the sending end system becomes impaired. Next, coming to the improvement of transient stability. Improvement of transient stability. So up to now we discussed about the two objectives of the reactive shunt compensation, and next coming to the improvement of transient stability. This is also one of the main objective of the shunt compensation. So here the reactive shunt compensation can significantly increase the maximum transmittable power. You know this point. Thus, it is reasonable to expect that with suitable and fast controls, shunt compensation will be able to change the power flow in the system during and following dynamic disturbances. Okay, so as to increase the transient stability limit and provide effective power oscillation damping. So actually the transition stability means, the ability of the system to bring it to a stable or normal condition after the system is being disturbed. That is called as stability. Actually, we have three types of stability. One is steady state stability, and another one is transient state stability, and third one is dynamic state stability. So the transient state stability, what is meant by the transient state stability? So the transient state stability is the ability of the system to bring it to a normal or stable condition after a large disturbances. So the large disturbances means sudden load changes, sudden changes in the load, okay, and switching operations, like that we have. So to increase the transient stability limit and provide effective power oscillation damping, we are using the different fast controls and uh, different fast controls we are used for the shunt compensation. Next, the potential effectiveness of shunt on transient stability improvement can be conveniently evaluated by the equilibrium criterion. So equilibrium criterion, this equilibrium criterion is used to determine the maximum power limit of the system, maximum transmissible power of the system. Okay. So the meaning of the equilibrium criterion is explained with the aid of the simple two machine system. So here I am taking a simple two machine system. It consists of the receiving end is an infinite bus. The receiving end consists of the infinite bus. Okay. Two line system shown in the diagram. So here I am taking two parallel lines. Each consists of series connection of the inductances with a value of XL. So here in one of the lines one fault is occurred. So if you observe this diagram, on the first line we have a faulted condition. So both sending and receiving end we have a transmitter and generators. Okay, at the sending end we have the sending end voltage. It consists of one transformer, and the transformer is connected to a transmission line, two line transmission line. Okay, two line system. So it consists of a 4 points, and on the receiving end we have a receiving end transformer, and we have a receiving end voltage, and the B diagram gives the equilibrium criterion for transient stability of a two machine system, two machine two line power system. Okay, so here we have two curves. Okay, here the curve is drawn between angle delta and power P. So here the angle is between 0 to pi, and the power is between 0 to P maximum. Here we are considering the two curves. One is for pre-fault and post-fault and during the fault. Okay. So here we have two areas, A1 and A2. Okay, A1 and A2. So assume that the complete system is characterized by the P versus delta curve A and is operating at angle delta 1 to transmit power P1 when a fault occurs at line segment 1. So assume that the complete system is characterized by the P versus delta curve, that is already shown in the diagram, curve A. Okay. So that means small a, that is a pre-fault condition. Okay. At that time, and is operating at an angle delta 1. If you observe this one, so this one delta 1. On the x-axis we have delta 1. Okay. It is operating at an angle delta 1. Why? Because to transmit the power P1, it is on the y-axis. Okay. When a fault occurs at a line segment, so when a fault occurs in a line segment, it transmits the power P1 at an angle delta 1. Okay, that is known as a pre-fault condition. That curve, and during the fault, the system is characterized by the same P versus delta curve B. So here one more curve is there, that is B. So this B curve is for the during the fault condition. So A is for the pre-fault condition, and B is for the during the fault condition, that is indicated with the B. So over this period, the transmitted electric power decreases significantly. So while mechanical input power to the sending end generator remains substantially constant corresponding to P1. So here the mechanical input power to the sending end generator remains substantially constant corresponding to P1. So as a result, the generator accelerates and transmission angle increases from delta 1 to delta 2, at which the protective breakers disconnect the faulted line system. Okay, as a result, the generator accelerates and the transmission angle increases from delta 1 to delta 2. If you observe the diagram, you will understand. So on the x-axis we have the different angles, 0 to delta. So in that one we have delta 1, delta 2 and pi by 2 and delta 3 and delta circuit and pi. Okay. So here as a result the generator accelerates and the transmission angle increases from delta 1 to delta 2, at which the protective breaker disconnects the faulted line segment 1. Why? Because the first line consists of a faulted condition. That's why the breaker disconnects the faulted line segment 1 and the sending end generator absorbs the accelerating energy represented by area A1. So the area which absorbs the accelerating energy is represented with A1. So if you observe the diagram, so in between delta 1 and delta 2 angles, we have that A1 area. So this one is used to absorb the accelerating energy from the sending end generator. And after fault clearing, that means post fault condition. Okay, after fault clearing without line segment 1, so there is no line segment 1, so the degraded system is characterized by the P versus delta curve, that is C. So A, B, C, we have 3 curves. So one is for the post pre-fault condition and another curve is for the during the fault condition and another curve for the post fault condition. So at an angle delta 2 on curve C, the transmitted power exceeds the mechanical input power Pi and the sending end generator starts to decelerate. Okay, so the angle is at delta 2 on curve C, the transmitted power exceeds the mechanical power P and the sending end generator starts to decelerate. So however, the angle delta further increases due to the kinetic energy stored in the machine. So the angle delta is further increasing. So the maximum angle reached at delta 3. Okay, so where the decelerating energy is represented by area A2. So in between delta 2 and delta 3 we have a decelerating area. It is indicated with the cross lines in between delta 2 and delta 3, that is represented with the area A2 and so and it becomes equal to the accelerating energy represented by area A1. That means in that condition we have A1 is equal to A2. A1 is equal to A2. So the limit of transient stability is reached at delta 3 is equal to delta CRT, that means delta critical or concentrated, beyond which the decelerating energy would not balance the accelerating energy and synchronism between the sending end and receiving end could not be restored. So the area A margin between delta 3 and delta circuit represents the transient stability margin of the system. So if you have the diagram, you will see. So here we have A margin. So capital A suffix margin. So this will indicates the area A margin between delta 3 and delta. So the area is in between delta 3 and delta circuit. It represents the transient stability margin of the system. Transient stability margin of the system. So it is evident that the transient stability at a given power transmission level and fault clearing time is determined by the P versus delta characteristic of the post fault system. Okay, so the transient stability at a given power transmission level and fault clearing time is determined by the P versus delta characteristic of the post fault system. So since appropriately controlled shunt compensation can provide effective voltage support, so it can increase the transmission capability of the post fault system, that is after the fault, and thereby enhance transient stability. So for comparison, the above introduced equilibrium criterion is applied here in a greatly simplified manner with the assumption that the original single line system shown in the diagram, that is in the first diagram of the objectives of shunt compensation, represents both the pre-fault and post-fault systems. Okay, so here I am taking the system with and without the midpoint shunt compensator. Okay, transmit the same steady state power. Okay, so this is the diagram I am taking. Okay, actually this is the first diagram, that is the 5.1 diagram. So in that one we have sending and receiving end voltages, means generators, and in between these two we are connecting a series transmission line. It consists of a series of reactance values. In between we have a midpoint voltage. It consists of a ideal compensator. So assume that both the uncompensated and the compensated systems are subjected to the same fault for the same period of time. So the dynamic behavior of these systems is illustrated in the figures. So in these figures are illustrated. Okay, equilibrium criterion to illustrate the transient stability margin. To illustrate the transient stability margin for a simple two machine system without compensation. That is the first diagram. And with an ideal midpoint compensator, that is the second diagram. Okay, with compensation, that is the left side of the diagram, and with compensation, that is the right side of the diagram we have. Okay, next, so prior to the fault, that means during the fault, both of them transmit power PM, that is the mechanical power, at angles delta 1 and delta P1 respectively. Okay, that is the prior to the fault. It transmits the power PM, that is the mechanical power, between delta 1 and delta 2. Delta 1 and delta 2. Okay. So delta 1 and delta P1, sorry, delta P1. So delta 1 and delta P1. Next, so during the fault, the transmitted electric power becomes zero. Okay, while the mechanical input power to the generators remains constant. Okay, remains constant. So therefore, the sending end generator accelerates from the steady state angles from delta 1 and delta P1 to delta 2 to delta P2. Okay, delta 2 to delta P2. So like this we have. So on the right side observe. So actually the angle is between delta to delta P1 and next it is moved to delta 2 to delta P2. Okay. So actually the diagram is between firstly delta 1 and delta 2 and after that it is moved to delta 1 to delta P1 and next it is moved to delta 2 to delta P2. Okay, next. So when the fault clears, the accelerating energies are represented by areas A1 and AP1. If you observe the two characteristic diagrams, that is two equilibrium criterion diagrams with and without compensation, so it gives the accelerating areas, A1 and AP1. So A1, that is on the left side of the diagram, and AP1 area is in the second diagram, that is on the left side we have without compensation and right side we have the with compensation. Okay. So when the fault clears, the accelerating energies are represented by areas A1 and AP1, and after fault clearing, the transmitted electric power exceeds the mechanical input power and the sending end machine decelerates. So but the accumulated kinetic energy further increases until a balance between the accelerating and decelerating energies corresponding to areas A1, AP1, A2 and AP2 respectively is reached at delta 3 and delta P3. Okay, after fault clearing, the angle is moving from delta 3 to delta P3. So in between we have the areas. Okay, next it representing the maximum power swings for the two cases. That is the condition where the maximum angular swings for the two cases. So the areas between P versus delta curve and the constant mechanical power line over the intervals defined by angles delta 3 and delta circuit and delta P3 and delta P circuit respectively. It determines the margin of transition stability. So that is the unused and still available decelerating energy represented by areas A margin and AP margin. These are the decelerating areas. Okay. So this is the explanation for those two diagrams, A1, A2 and AP1 and AP2. So this is the decelerating area margin. This is the one, and the power is P is equal to V square by X into sin delta. This is for the without compensation, and after with compensation we have PP is equal to 2 V square by XL into sin delta beta. That is the 2 times to the previous one. Okay, next. So comparison of those two diagrams clearly shows a substantial increase in the transient stability margin. The ideal midpoint compensation with unconstrained wear output can provide by the effective segmentation of the transmission line And alternatively, if the uncompensated system, that is without compensator system, has a sufficient transient stability margin, shunt compensation can considerably increase the transmittable power without decreasing this margin. So in this explanation of equilibrium criterion at the beginning of this section, a clear distinction was made between the pre-fault and post-fault power system. So it is important to note that from the standpoint of transient stability and thus of overall system security, the post-fault system is the one that counts. Okay. Next, so that is, power systems are normally designed to be transiently stable with defined pre-fault contingency scenarios and post-fault system degradation when subjected to major disturbance, that is fault. Okay, because of this design philosophy, the actual capacity of the transmission system is considerably higher than that at which they are normally used. Okay. So in the case of an underdamped power system, so coming to the power oscillation damping. Okay, coming to the power oscillation damping, there is the final objective of the static shunt compensation. So in the case of an underdamped power system, any minor disturbance can cause the machine angle to oscillate around its steady state value at the natural frequency of the total electromechanical system. Okay, so the angle oscillation of course results in a corresponding power oscillation around the steady state power transmission. Okay, so the lack of sufficient damping can be a major problem in some power systems, and in some cases it may be the limiting factor for the transmittable power. Okay, since power oscillation is a sustained dynamic event, it is necessary to vary the applied shunt compensation and thereby the midpoint voltage of the transmission line to counteract the accelerating and decelerating swings of the distributed machine. Next, that is, when the rotationally oscillating generator accelerates and angle delta increases, that is d delta by dt greater than 0, so the electric power transmitted must be increased to compensate for the excess mechanical input power. So when the generator decelerates and angle delta decreases, so when the generator accelerates, the angle delta increases. So when the generator decelerates, angle delta decreases, that is d delta by dt is less than 0. The electric power must be decreased to balance the insufficient mechanical input power. Okay. Next, the requirements of wear output control and the process of power oscillation damping is illustrated in the waveforms, that is always shown in the next diagram. Okay, the waveforms in the diagram show the undamped and damped oscillation of angles delta around the steady state value delta naught. So this one. Here we have three diagrams. So the first diagram is for the waveforms illustrating power oscillation damping by reactive shunt compensation. Okay, next, the B diagram, the A diagram is for the generator angle. So the A diagram is for generator angle and B diagram is for transmitted power, and the third diagram is for wear output of the shunt compensator, wear output of the shunt compensator. So the diagrams is like this. So the first diagram is for the generator angle, that means delta versus T, and the second diagram is for the P versus T, and the third diagram is for the Q versus T. So here we have two waveforms. One is for the undamped system and another is for the damped system. So for the generator angle, we have the waveforms like this, and for the transmitted power, we have the waveforms like this, and for the reactive power, that means wear output of the shunt compensator, the waveform is like this, from sine wave to square wave we have like this. Okay. Next, so from the waveforms in the figure B, that is from the B, show the undamped and damped oscillations of the electric power P, that is the B diagram, B waveform around the steady state value P naught, and the waveform C shows the reactive power output, that is QP of the shunt connected wear compensator, and the capacitive output of the compensator increases the midpoint voltage and hence the transmitted power when d delta by dt is greater than 0, and it decreases those when d delta by dt is less than 0. So as the illustration shows, the wear output is controlled in a bang manner. So that means output is varied between the minimum and maximum values. So this type of control is generally considered the most effective, particularly if large oscillations are encountered. Next, so however, for damping relatively small power oscillations, a strategy that varies the controlled output of the compensator continuously in sympathy with the generator angle or power may be preferred. That means the first one or the second one will be preferred. Next, the functional requirements of the reactive shunt compensators. Coming to the last one, that is summary of compensator requirements. So this is the brief explanation for the four objectives. Okay, so the functional requirements of reactive shunt compensators used for increased power transmission. So improved voltage and transient stability and power oscillation damping can be summarized as follows. That means the compensator must stay in synchronous operation with the AC system at the compensated bus under all operating conditions include major disturbances. So that should be the bus voltage be the lost temporarily due to nearby faults. So if the fault occurs or the nearby the fault, the bus voltages are lost temporarily, then the compensator must be able to recapture synchronism immediately at fault clearing. Okay. Next, so the compensator must be able to regulate the bus voltage for voltage support and improve transient stability or control it for the power oscillation damping and transient stability enhancement on a priority basis as system conditions may require. So for a transmission line connecting two systems, the best location for wear compensation is in the middle, whereas for a radial feed to a load, the best location is at the load end. Okay, so as will be seen, all of the solid state approaches for wear generation and control discussed in this one can meet the steady state and dynamic compensation requirements of the power systems. So however, there are considerable differences in the functional characteristics and achievable response times as well as in their evaluated capital and operating cost related to space and installation requirements and loss evaluation criteria. So this is a summary of compensator requirements. Okay, thank you. Thank you for watching this video. So in the next class, I'm going to discuss remaining one, that is the methods. Okay.